Let us next see this theorem. This is going to be an application of Wilson's theorem, and it's about the solvability of this quadratic congruence x square plus 1 congruent to 0 modulo p, where p is an odd prime. And the claim is that it is solvable, it has a solution if and only if p is congruent to 1 modulo 4. In other words, if you divide p by 4, then you get the remainder 1. So let us see the proof. Because it's an if and only if statement, so there are two implications to prove. Let us first assume that the congruence has a solution. We then have to prove that p is of this form, and then we will prove the converse. Let the integer a be a solution of the given congruence. Then what will happen then? A square plus 1 is congruent to 0 mod p. That is, a square is congruent to minus 1 mod p. Now note that p does not divide a. Why? Because if p divided a, then the left hand side of this congruence would be itself congruent to 0, and we would get 0 congruent to minus 1 modulo p, which is not true because p does not divide 1 or minus 1. Now, p does not divide a. So, by Fermat's theorem, so we see that Fermat's theorem is also being used, but that's not a problem. A to the power p minus 1 will be congruent to 1 modulo p. Okay. Now, what can we say about the, how can we link this congruence and this congruence? Let us start with 1. 1 is congruent to a to the power p minus 1. The modulus, of course, is p, that's understood. We will write it finally. Now you can write this a to the power p minus 1 as this. Does it make sense? Are we still talking about integers? Are we dealing with integers? Yes, 2 of course is an integer. How is p minus 1 divided by 2 itself an integer? Well, if you can actually write like this, but after that you won't be able to do anything if this exponent is not an integer. Luckily it is, because p is an odd prime, so p minus 1 is even, and that is why when you divide that by 2 you ultimately get an integer. And that is why you can now write in place of this a square minus 1. Modulo p. Okay. Now we know that this p minus 1 divided by 2 will be an integer. However, what type of integer? Since p is odd, so obviously p will not be of the form 4k or 4k plus 2, because these are even integers. That means p is either of the form 4k plus 1 or 4k plus 3. Or p is equal to 4k plus 3, where k is an integer, that's understood. If p is 4k plus 3, then what will happen to p minus 1 divided by 2? That is 4k plus 2 divided by 2, or 2k plus 1. So that means p minus 1 over 2 is 2k plus 1, and so it's odd. But then what happens to this congruence? The left hand side of course is 1, and what will happen to this right hand side? Because this is after all an odd integer, so having an odd exponent over minus 1, it will be minus 1. Or p has to divide 2. That however is not possible, because p is an odd prime, so p is greater than or equal to 3. So how can it divide 2? There is only one prime which can divide 2, which is 2 itself. Which is not possible. And that is why this option is ruled out. We cannot have this. Hence, we can only have p equal to 4k plus 1. i.e., if you write that in term as a congruence, then you get this: p is congruent to 1 modulo 4. So we have shown one half of our claim. Conversely, let p be equal to 4k plus 1 for some integer k. Alright. Now note that we have these congruences. Let us start with p minus 1. P minus 1 of course is congruent to minus 1 modulo p, because p divides p. Just like that, p minus 2 is congruent to minus 2 modulo p. And if you continue like this, you get p minus 1 divided by 2 is congruent to minus p minus 1 divided by 2 modulo p. Okay, and again, because p is odd, p minus 1 divided by 2 is an integer, in fact a positive integer. Alright, now how can we use these congruences? In this half of the proof, we are going to use Wilson's theorem. That is why it's an application of Wilson's theorem. Now, by so what does Wilson's theorem say? It says that p minus 1 factorial is congruent to minus 1 modulo p. So let us start with minus 1. Minus 1 is congruent to p minus 1 factorial. Now if we expand p minus 1 factorial, it's going to look like this, of course. P minus 1, p minus 2 and like that it will go. At some point we will get this. We are going on subtracting larger and larger integer, right? At one point we will subtract p minus 1 divided by 2, alright, and then we will subtract one more. One more means to this p minus 1 divided by 2 you would add 1, and that sum you will subtract from p in the next factor. So what will that sum be? P minus 1 divided by 2 plus 1. So if you do the little calculation, you get this, p plus 1 divided by 2. That means in the next factor we get this, okay. And then still it doesn't stop there, it continues, and eventually we get 2 and 1, okay. Now here's the thing, you can replace these things by these things. So that means half the factors will get replaced by some other integers. For example, in place of this first one you will write minus 1, in place of this you will write minus 2, and like that it goes. In place of this you would write minus p minus 1 divided by 2. In order to really be sure of what we are writing, I am using extra sets of brackets. Now what is this actually? If I do the calculation here, I mean ordinarily just if I do the calculation, it will be 2p minus p minus 1, that means p minus 1 divided by 2. And then of course the next factor comes, and eventually we have 2 times 1. If you want, you can write one more factor here. If you do, you will see that you are getting a number, an integer here, I mean the one that should come after this factor, whereas the factor that comes before this one is the negative of that. That is how actually you see we are getting these 1, 2, 3 up to p minus 1 divided by 2 and their negative versions here. So there are repetitions. And in this total product, there are as many negatives as there are positives. But how many negatives do we have? This many, p minus 1 divided by 2. So if I now take the negatives together, the minus 1's together, I will get minus 1 to the power p minus 1 divided by 2. And then you consider the integers which got repeated. Okay, each one gets repeated, and that is how you get 1 times 2 times this square. Okay, now what was our original p? Our original p was 4k plus 1. Okay, let me do the little calculation here. Then what happens to p minus 1 divided by 2? So 1 and minus 1 cancel each other and you get 4k over 2, that is 2k. That means this exponent is an even integer, so it becomes plus 1. However, what do we have under the square here? P minus 1 divided by 2 factorial and the square of that modulo P. Considering the fact that we have minus 1 on this side, you can finally write that is P minus 1 divided by 2 factorial square plus 1 is congruent to 0 mod P. So yes, we have shown that this congruence x square plus 1 congruent to 0 mod P really has a solution, and this is an explicit solution. That means the congruence is solvable, and this completes the proof of the theorem. The author has given one example where he has taken P equal to explain this entire thing. In a concrete case, he has taken P equal to 13. Then what do we get? I mean, if this is given, and then you have to check if it is of the form 4k plus 1. Yes, it is, because this is 4 times 3 plus 1. That means for this prime also the congruence x square plus 1 congruent to 0 mod 13 has a solution, and this is one solution. So we can see what the solution is in this special case. So for this prime, what is P minus 1 divided by 2? P minus 1 divided by 2 is 12 divided by 2, that is 6. That means our solution is 6 factorial. This is x, no? This is x, and we want x square plus 1 to be congruent to 0 mod P. So the x here is 6 factorial, which is 720, and you can calculate yourself that it becomes congruent to 5 modulo 13. You divide 720 by 13, the remainder is 5. Now let us also see if 5 really satisfies. Well, I mean, you can take 720 here itself, but because 720 itself is congruent to 5, so a better and more manageable solution is 5. Now what is 5 square plus 1? 25 plus 1 is 26. Is it divisible by 13? Yes. 2 times 13 is 26. So this is congruent to 0 mod 13. So not only do you have the fact that for such primes this congruence is solvable by, but you can find a concrete solution by following this procedure. You know what a solution is. And finally, there is one remark that the author makes. You see, Wilson's theorem gives us a fact about composite numbers. What it says is that, let us recall Wilson's theorem. What Wilson's theorem says is that P divides P minus 1 factorial plus 1. Because this number obviously is greater than P. So the fact, I wrote does not divide. What the hell? P divides. Because this P divides this number which is greater than P itself, it becomes composite. And there are infinitely many primes, so that way we get infinitely many composite numbers of this form, that is n factorial plus 1. However, the corresponding question for primes, that are there infinitely many primes of this form, is still open. It's unknown whether there are infinitely many such primes or finitely many. These are called, they have a name also, these are called factorial primes. The prime numbers which are of this form, and also actually n factorial minus 1 is called a factorial prime. So the open question is whether there are infinitely many factorial primes, and the author gives us some numbers of this type which are prime. If n lies between 1 and 100, then n factorial plus 1 is prime for these values of n. 1, 2, 3, then 11, 27, 37, 41, 43, oh sorry, not 43, 73 and 77. So you can see that it's not necessary that n itself has to be prime. I mean, the first few values make you think like that, but this is not a prime. So these are the n values between 1 and 100 for which n factorial plus 1 is a prime, it's a factorial prime. And finally, the author also gives us the example of the largest prime of this type that was available at the time of writing the book, which is this 1477 factorial plus 1. It's known that this is the prime. This will be a gigantic number, and it was found in 1984. However, it has been surpassed. Okay, the current record holder is another far larger number, 2429 factorial plus 1. This was found in 2022. There is an even larger one, I think, which is of that other form, n factorial minus 1. Okay, but this is the largest of this form. If you want to keep track of these things, you visit this website, t5k.org/top20. Okay, so you visit this website and there you will see many different types of numbers, and the largest of the type that so far are known. Okay, so if you want, if you are interested, you can visit this website. There are many such websites which give us information about different parts of mathematics, and they help you be up to date with things. For example, at the just now I said that this was the largest at the time of writing this book, but it's been so many years, and the current largest is this one. Okay, so with that we are going to end today's video, and tomorrow we have differential equations. Okay, because last week we did topology, so tomorrow differential equations. So that will be all. So see you tomorrow with differential equations. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.